heat capacities of solids. Now, a solid consists of a regular array of atoms and are connected by intermolecular forces which can be approximated as spring connections, like this. This is what I have shown you what a solid is like. The molecules can vibrate about their main positions. That means they behave as though each molecule is connected to its neighbor by spring connections like this. Now, these atoms, in addition to their translational motion in the x, y, and z directions, also vibrate in x, y, and z directions. That means each solid atoms have 6 degrees of freedom. So, thus an atom in a solid has 6 degrees of freedom. And what is the energy associated with each degree of freedom? Is 1/2 kT. We have said this now numerous times. I don't think you can forget. The energy associated with 1 degree of freedom is 1/2 kT. Therefore, the molar heat capacity of a solid is 3R. Well, this agrees well with experimental observations. That means all our theoretical considerations have been verified experimentally, and we are in good grounds. This relation is actually called Dulong-Petit law, that the molar heat capacity for all solids is 3 times R. Okay, let's do a problem. 1 mole of an ideal diatomic gas. See, when you look at diatomic gas, you must say CMP is 7/2R, CMV is 5/2R. Is heated at constant volume from 300 to 600 Kelvin. Find the increase in internal energy, the work done, and the heat added. Find the same quantities if this gas is heated from 300 to 600 Kelvin at constant pressure. Well, first we have the increase in internal energy. Remember, increase in internal energy is dU. And you know, dU by dt is what we call CV. So dU equal to CV times dt. For a diatomic gas, CV equal to 5/2R, and dt is given to be 600 minus 300, and that is 300 Kelvin. So what is the increase in internal energy? dU equal to 2.5R. CV is 2.5R times dt. That will be 2.5 times 8.314 times 300, and that is 6,236 joules. What's our B part? Now, because the heat is added at constant volume, the work done dW equal to 0. So we found the increase in internal energy and the work done. Remember, when there is no change in volume, there is no work done. Now, the quantity of heat added, dQ equal to dU plus dW. dU is this 6,236 and dW is 0. Therefore, dQ is the same quantity, 6,236. Alright, find the same quantities if this gas is heated from 300 to 600 Kelvin at constant pressure. What is the difference? Since the change in temperature is the same, the change in internal energy remains the same. We don't need to go and calculate it again. The change in temperature is from 300 to 600. The internal energy is solely due to the change in temperature. So that will not change from the previous problem. Well, work done is given by, what is the work done when the pressure is a constant? Well, W is integral V1 to V2 of PdV, which when the pressure is a constant is P times V2 minus V1. Is that right? An isobaric process. The pressure is a constant in this case. And we have N equal to 1, PV equal to RT. And since P is a constant, we have PV1 equal to RT1. Is that right? Because PV equal to RT, PV1 equal to RT1, that is take 1, and PV2 equal to RT2. You understand these relations? Pressure is a constant. It changes from state 1 to state 2. You see? And we have PV1 equal to RT1 and PV2 equal to RT2. We are looking for PV2 minus PV1 is the work done. Can you obtain that from here? Well, P times V2 minus V1 equal to R times T2 minus T1. Did you understand that? Look at this. P times V2 minus V1 means PV2 minus PV1. PV2 minus PV1 is RT2 minus RT1. That's what we have here. R times T2 minus T1. Now, you know these quantities. W, the work done, equal to P times V2 minus V1, which is the same as R times T2 minus T1. And we know those quantities. R is 8.314 times T2 minus T1 is 300, and that is 2,494. And therefore, dQ, the heat added, dQ equal to du plus dW, and that will be 8,730 joules of heat. A very, very important type of problem. Let's do another one. 1 mole of a monoatomic ideal gas is initially at 273 Kelvin and 1 atmosphere of pressure. What is the initial internal energy? Find its final internal energy and the work done when 500 joules of heat are added at constant pressure. Find the same quantities when 500 joules of heat are added at constant volume. Alright, we got T1 equal to 273 Kelvin. P1 is 1 atmosphere, convert that to Pascal, 1.01 times 10 to the 5 Pascal. And N equal to 1. What do we need to find? We need to find the initial internal energy. And for a monoatomic gas, the internal energy is 3/2 nRT. Now what are the things that we have? Do we have the temperature? Yes. So that will be 3/2 is 1.5 times N is given 1 mole times R is 8.314 and the temperature is 273. So the internal energy of the gas at constant volume is 3,405 joules. Alright? Find its final internal energy and work done when 500 joules of heat are added at constant pressure. Alright? When heat is added at constant pressure, dQ equal to Cp dt. Is that right? Because the definition of Cp is dQ over dt. Now 500 equal to Cp for a monoatomic gas. Cp for a monoatomic gas is 5/2 R, which is 2.5 R times dt. And that will lead you to dt, the change in temperature. So we can now find the change in temperature dt. How? dt, therefore, see, 2.5 R dt is 20.79 dt. 2.5 times 8.13 is this. So 500 equal to 20.79 dt. Therefore, dt equal to 500 divided by 20.79, and that is 24.05 Kelvin. Now the increase in internal energy is du equal to Cv dt. And that will be Cv is, for a monatomic gas, Cv is 3/2R multiplied by dt is 24.05, and using R equal to 8.314, we have that as 300 joules. The increase in internal energy is 300 joules. So the final internal energy is original internal energy plus the change in internal energy, and that is 3705 joules is the final internal energy. I want you to practice these kind of problems. dq equal to du plus dw, and we need to find the work done. dw equal to dq minus du. That will be 500 minus 300 equal to 200 joules. Alright? C. Find the same quantities when 500 joules of heat are added at constant volume. The only difference is when heat is added at constant volume, there is no work done. Therefore, all the heat added goes into increasing the internal energy. Therefore, du equal to 500 joules and dw equal to 0. Okay, well, I want you to practice these kind of problems. I'm going to stop this part of the lesson here. I will come back to you with the second part of this lesson a little later. To apply